All right, let's get into it. We're going to dive into the two main tools in this nanoscale architect's toolkit. They're called solvothermal and hydrothermal synthesis. Now, they sound super similar, I know, but trust me, one tiny difference between them opens up a whole world of possibilities.
So first up, we've got solvothermal synthesis. Okay, picture this. You're a chef, and you have these ingredients that just do not want to mix or react. This method is how you persuade them. You take your starting materials, your precursors, toss them into an organic solvent, and seal them up in this super strong container called an autoclave. Then, you just crank up the heat. The pressure inside gets so intense that it forces everything to dissolve and react in completely new ways. It's chemistry by force.
Okay, now what if you take that organic solvent and just swap it out for plain old water? Well, when you do that, the method gets a special name: hydrothermal synthesis. It sounds like such a simple change, right? Just one liquid for another. But as you're about to see, that single choice changes absolutely everything.
So the basic recipe for both of these methods is pretty straightforward. You mix your starting chemicals, the precursors, in a solvent. Then you seal the whole mixture inside this tough, Teflon-lined steel container, the autoclave. Then you heat it up, and as it gets hot, the liquid inside wants to expand, but it can't because it's sealed, so it generates its own insane pressure. And it's in that extreme environment where the magic happens. Atoms can finally arrange themselves into these beautiful, highly ordered, perfect crystalline structures, things you just couldn't make any other way.
So yeah, the single biggest difference, the thing that separates these two incredibly powerful methods, it all comes down to one simple choice. What liquid do you put in the pressure cooker?
You've got two paths. On one side, you've got hydrothermal synthesis, which, just uses water. And on the other, you've got solvothermal, which uses all sorts of different organic solvents that aren't water. And this choice, this fork in the road, creates a fundamental trade-off for any chemist trying to build these materials.
And here's what that trade-off looks like. Hydrothermal, that's your green chemistry option. I mean, it uses water, it's safe, it's everywhere, it's environmentally friendly, but solvothermal, on the other hand, can get a lot hotter. And those organic solvents are way better at dissolving some of the more complex, tricky ingredients. And that means you get much finer control over the final crystal's size and shape.
So that's the bottom line, right? Chemists are always having to weigh their options. Are we going to prioritize a green, safe, low-cost process, or do we need the absolute best performance, the most versatility to get exactly the final structure we want? It is a constant balancing act.
But wait, there's more. The solvent isn't the only knob they can turn. Oh no. Beyond that first big choice, chemists can act like real nanoscale architects, tuning a whole bunch of other parameters to get exactly what they want.
The general workflow is pretty much what you'd expect. You combine your precursors, add the solvent, and maybe some special additives. Seal it, heat it, let it cool down, and then you filter and dry your shiny new crystals. Easy, right? But the real magic, the artistry really, that happens when you start messing with the details in that recipe.
And here are all those little knobs you can turn. How hot do you make it? How long do you cook it for? What exactly are your starting ingredients? Do you throw in a little something extra, like a surfactant, to help guide the shape, or a reductant to tweak its chemistry? Even something as simple as the pH level can completely change the final product. By playing with all these variables, scientists can pretty much dictate the material's final shape, its size, and even its electronic properties. It's incredible.